The recent excitement in the astronomical community has not been limited to the interstellar visitor 3I/Atlas. Another celestial object, the historically significant comet 12P/Pons-Brooks, has once again moved into the spotlight, drawing the curiosity of scientists around the world. First discovered in 1812 by astronomers observing its luminous tail cutting across the night sky, this comet has long been known for its roughly 71-year orbital period and its tendency to produce sudden bright outbursts. Each of its returns has offered opportunities to study the behavior of icy bodies that wander the outer solar system, but its most recent appearance during 2024 has delivered new kinds of revelations that extend far beyond simple visual observations. What makes 12P particularly fascinating this time is the discovery of unusual radio signals emanating from it, detected during its approach to the Sun. These signals, measured with extraordinary precision, have opened the door to a deeper understanding of the comet's internal chemistry, the processes driving its eruptions, and even the bigger story of how water and organic molecules may have helped shape the early Earth billions of years ago. A team of astronomers from the Shanghai Astronomical Observatory, part of the Chinese Academy of Sciences, embarked on an extensive study using data from the Tianma radio telescope. This telescope, known for its high sensitivity and ability to observe different radio wavelengths, monitored the comet throughout its journey around the Sunday 12P/Pons-Brooks, is classified as a Halley-type comet, a category that includes objects with orbital periods between 20 and 200 years. These comets spend most of their time in the distant reaches of the solar system, but occasionally make a dramatic sweep near the Sun, giving scientists brief windows to study their volatile behavior. The last time 12P came near Earth was in 1954, and records show that during each of its close passes, it has exhibited sudden increases in brightness and unexpected radio wave emissions. What makes these flare-ups especially intriguing is that scientists still do not fully understand what triggers them. The comet appears calm for long stretches of its orbit, and then, with little warning, erupts in a burst of activity bright enough to be seen from Earth. During the 2024 approach, the Tianma observations revealed something remarkable: a noticeable spike in the spectral line associated with hydroxyl, a radical formed when water molecules are broken apart by solar radiation. Hydroxyl emissions are a key indicator of how comets release gas as their ice heats up and sublimates, and detecting such a strong signature suggested that 12P was releasing water vapor at a very high rate. By running detailed computer simulations, the research team analyzed how sunlight interacted with the comet's surface and calculated how its water production changed during each outburst. Their models showed that 12P is significantly more active than most Halley-type comets previously studied, which raises new questions about what lies beneath its dark, icy exterior. This level of activity is far from trivial. Comets are often considered frozen relics from the earliest days of the solar system, left over from the time when planets were still forming 4.6 billion years ago. By measuring the gases and particles they eject, scientists can reconstruct conditions that existed long before Earth developed oceans, continents, or life. The water, organic molecules, and minerals released from comets may represent the original building blocks that contributed to Earth's early environment. Some theories even propose that comets delivered a significant fraction of Earth's water through repeated impacts during the planet's chaotic youth. Because of this, every time a comet like 12P reveals unexpected behavior or unusual chemical signatures, it provides valuable clues about how life-supporting conditions emerged on our planet. As 12P drew closer to the Sun in 2024, it brightened dramatically, capturing the attention of both professional astronomers and casual skywatchers. The Tianma radio telescope focused specifically on L-band and K-band radio waves, which are ideal for detecting certain molecules in the comet's coma, the cloud of gas and dust surrounding its nucleus. One of the most astonishing findings was the measurement of water vapor output. At a distance of 1 astronomical unit, the same distance separating Earth and the Sun, the comet was releasing more than 5 tons of water vapor. This rate is extraordinary compared to both short-period comets, which return frequently, and long-period comets that take thousands of years to complete an orbit. Such a high volume of water vapor suggests that the comet possesses large reservoirs of subsurface ice or pockets of volatile material that are triggered into activity when solar energy penetrates its surface layers. Even more surprising was the detection of ammonia molecules, marking the first time ammonia has ever been conclusively identified in a Halley-type comet. Ammonia is an important organic compound, one that plays a role in forming amino acids and other precursors to biological chemistry. The researchers noted that the ammonia spike appeared during one of the comet's outbursts, hinting that an internal reservoir of volatile substances may be directly involved in triggering these explosive events. If ammonia and other compounds are sealed beneath layers of ice and dust, they could rapidly expand when heated, causing sudden ruptures and bright flare-ups. This theory links the comet's chemistry to its physical behavior in a way scientists had long suspected but rarely observed directly. The discovery of ammonia also connects to broader questions about the origins of life on Earth. If comets like 12P contain organic molecules that resemble those needed for biological development, they may have acted as natural delivery systems billions of years ago. Ammonia mixed with water can drive chemical reactions that eventually lead to more complex organic compounds, and the presence of such materials in a Halley-type comet strengthens the case that early Earth may have been seeded with essential ingredients from multiple cometary impacts. Earlier this year, another major study added even more weight to this hypothesis. Led by NASA Goddard Space Flight Center researcher Martin Cordner, the team analyzed water from 12P and discovered that its isotopic signature, the ratio of hydrogen to its heavier form, deuterium, was almost identical to that found in Earth's oceans. This is significant because many comets studied in the past have water with very different isotopic ratios, suggesting that not all comets contributed equally to Earth's water supply. The fact that 12PS water closely matches Earth's supports the idea that at least some comets of its class may have delivered water that ultimately became part of our oceans. Cordner emphasized that the new results provide the strongest evidence so far that Halley-type comets played a role in making Earth habitable. When taken together, the CHEMA observations and the isotopic findings paint a picture of a comet far more dynamic and chemically rich than previously imagined. They reveal a body that not only contains water similar to Earth's, but also stores complex molecules that may help explain the origin of organic chemistry in the solar system. The immense water vapor output shows that the comet continues to undergo dramatic transformations as it interacts with solar heat, exposing deeper layers and releasing compounds that were likely formed billions of years ago. Its powerful outbursts, once viewed as unpredictable flashes of brightness, now appear to be windows into the subsurface reservoirs that hold the secrets to its composition. The renewed attention on 12P/Pons-Brooks has also highlighted how advancements in radio astronomy are reshaping comet science. Instruments like the CHEMA radio telescope can detect fine details in radio emissions that were impossible to measure just a few decades ago. These tools allow astronomers to monitor changes in a comet's chemistry in real time, tracking how specific molecules appear, rise, or vanish over short periods. This approach complements traditional optical observations, providing a more complete picture of a comet's physical and chemical evolution. As 12P continues its journey away from the Sun and back toward the outer regions of the solar system, scientists will keep studying the data collected during its 2024 passage. Its next return won't occur for many decades, making the information gathered now especially valuable. The findings already achieved: strong hydroxyl signals, unusually high water production, the first detection of ammonia in a Halley-type comet, and Earth-like water isotopes, underscore how much this single object can teach us about the mysteries of our solar origins. Each discovery adds another piece to the puzzle of how planets formed, how water arrived on Earth, and how the ingredients for life may have been transported across space. For now, Comet 12P/Pons-Brooks stands not just as a spectacular visitor in our skies, but as a scientific treasure, offering insights that stretch back to the dawn of the solar system. Its unexpected radio signals and chemical fingerprints remind us that even centuries after its discovery, this comet still holds secrets waiting to be uncovered, pushing astronomers to keep searching, questioning, and exploring the deep history written in these ancient ice-covered wanderers.